Thanks, Gary. Okay, let's get this started. Slideshow, come on, there we go. Okay, good evening, everyone. My name is Jim Wilcox, and my presentation is entitled A Delicate Sound of Thunder, Building a Sound Shed and View Shed of the Late Bronze Age Eruption of Thera. This evening, I'm going to tell you about my research. I will go over some background for context. I will cover my methods and results. I will discuss those results, wrap it all up in a thrilling conclusion, and then finally touch on further steps to be taken. An eruption needs a volcano. This volcano is Thera, also called Santorini. It's a small crescent-shaped island in the Cyclades, a little north of Crete and southeast of Athens. The main industry is tourism, and there are a little over 15,000 permanent residents. They say it's an island, but it's actually an archipelago of 5 islands. The two large ones, Santorini and Thracia, are where everybody lives. The central lagoon is made up of 2 calderas. The southern one is about 21,000 years old, and the northern one is the subject of this evening's discussion. Now, where there's a caldera, there's an eruption. The one we're interested in happened toward the end of the Bronze Age, sometime between 1600 and 1500 BCE. Notice the asterisk, that will be important later. The late Bronze Age eruption of Thera was one of the largest in human history. Well, how big was it? It blasted out more than 80 cubic kilometers of rock, lava, and ash into the stratosphere, the island, and the eastern Mediterranean. This gives it a volcanic explosivity index, VEI, of 6.9 or 7. To put this into perspective, Krakatoa in 1883 was a 6. Mount Vesuvius in AD 79, which destroyed Pompeii, was a 5. The 5,600 BC eruption that created Crater Lake in Oregon was a 7.0. This was gigantic. So the phases of this eruption went something like this. First, there was a precursor that dropped a lot of ash in the city of Akrotiri and convinced the residents to leave the island before it got any worse. And that was wise, because next came a Plinian eruption that shot vast quantities of ash and pumice into the stratosphere, 35 to 41 kilometers high. Soon, phreatomagmatic explosions joined the Plinian column as seawater breached the vent. This was followed by pyroclastic surges, and then the collapse and flooding of the caldera. So why is this eruption so important? Tephra and ash from this eruption is a horizon in archaeological sites across the whole region. If this eruption could be securely dated, it would be a fixed point in time that could link chronologies from Egypt, Greece, the Levant, and Asia Minor. Understandably, and this is where that asterisk from earlier comes in, there is considerable debate over the eruption date. I'll only lightly touch on this. Sturt Manning wrote a 500-plus page book about this debate in 1999, and it's just grown since. There are basically 2 chronologies. One is around 1600 BCE, and the other around 1500 BCE. Physical evidence, like absolute dating methods and archaeology, can support both sides and has been used to support both sides. Usually in a case like this, we can turn to written records. Unfortunately, there aren't many, and what we do have are open to interpretation and controversy. So the solution to that is more records. With more records, we are more likely to find ones with clear references to this eruption, as well as references to kings' names, festivals, floods, or other datable events. GIS can help with this. We can tell archaeologists where to look for records and give them some idea what may be in those records. Which leads me to the meat of this evening's presentation, the objective of my research. What would the eruption of Thera have looked like and sounded like, and who would have seen and heard it? So let's get to it. My study area covers the eastern Mediterranean from Sardinia to Iraq and southern Egypt to the Black Sea. I chose this area because it contains the territory of the literate cultures of the region that had a reasonable chance to witness the eruption. Now, I know I was going to be generating a sound shed and a view shed of the eruption, but that's kind of like looking at a map of high temperatures. You kind of need references, places where you can put numbers on the data. So I chose 39 roughly contemporaneous archaeological sites, like cities or towns, from all over the study area as best as I could. Now, all research has methods to its madness, and these are mine. First, some generalities. All my data was generated using ArcGIS Pro 2.5 or Python 3.6. All of my maps use the Europe equidistant conic projection because when distances are important, you go conic. My research objective had two halves, audio and visual. So let's begin with the audio, the sound shed. This was by far the most complex of the two and took the lion's share of the time. I needed a sample grid that I would then assign values to by calculating attenuation. I would then have to generate a sound surface by interpolation and lastly sample that surface at my study points. I used the Create Fishnet tool to create a 100 kilometer by 100 kilometer sample grid. Now, I noticed that there was not a point near Thera, which would skew my data somewhat. So I shifted the grid to correct it. I chose 100 kilometer by 100 kilometers as a reasonable compromise between detail and unwieldy numbers of points. Even at 100 kilometer spacing, there are 660 data points. Attenuation is the reduction of volume of a sound caused by air and distance. It's affected by the frequency of the sound, so the higher the frequency, the more attenuation occurs, and also by air density. Thicker air transmits sound better, so high pressure, low temperature, or high humidity reduce attenuation. Since distance also plays such a large part in attenuation, I used the near tool to calculate the distance between each sample point in Thera, and then added those fields to their table. As far as for frequency, the human hearing spectrum runs from 20 hertz to 20 kilohertz. It would be really time consuming to calculate attenuation for each of those frequencies, but I didn't have to. The spectrum can be broken up into 10 bands or octaves, which are named for the central frequency. I added 10 fields to the sample points table, one for each octave. Then I used a Python script to calculate the volume at each sample point. First, it calculates the atmospheric absorption in decibels per kilometer for each given octave. In this case, for the example, it's 31 hertz. For the calculations, I kept the same air density throughout. In the second portion of the script, it subtracts the absorption and the inverse square attenuation from a starting volume of 230 decibels to arrive at a volume for that sample point. This is all done via field calculator. Fairly rapidly, I was getting negative numbers at sample points. Since you can't get quieter than 0, I replaced negative values with 0 with this script in the field calculator. And I did this 10 times, once for each octave, changing the octave values in the script each time. Now that I had a grid of values, I could build an interpolation surface. I chose IDW since it's conservative and I wouldn't end up with interpolated values higher or lower than my sample values. I generated an IDW surface for each octave band. Finally, I used the sample tool to measure the volume at each of the study sites for each octave. Now to address the other half of my research objective, the visual side. I handled this by building a view shed, which was a much more straightforward process. I needed a DEM to make the view shed. Then I could sample the view shed at the study locations to see if they could see the eruption. I started out with 4 30 arc-second areas of mean elevation data from the USGS Global Multi-Resolution Terrain Elevation Data 2010 project, or GM10. I mosaicked them together into a single raster and clipped it to the study area. I added a field to Thera's attribute table and gave it a height of 41 kilometers, which was the maximum estimated cloud height. And then I ran the viewshed tool. The Earth curvature correction is very important. My first viewshed covered half of Europe and a good chunk of Africa because I forgot to use the curvature correction. And then once again, I sampled the viewshed to determine which study sites could see the eruption. So what did all that work get me? Same as before, I will start with the audio. Here's a chart showing the volume in decibels for some common sounds from very quiet to incredibly loud. And on the right-hand column, it has a permitted exposure for hours per day. And as you can see, it ramps up pretty rapidly at higher volumes. I use this information to symbolize the sound shed into 8 categories, from lowest to highest volume. Again, this is a compromise between resolution and the useful number of classes. At 31 hertz, the whole study area experienced a volume of at least 120 decibels, which is painfully loud. One thing to bear in mind, areas at the outer edge of a band are at the low end of that volume range, while areas near the inner edge will be at the high end. Now, an area from Thapsus in the west to just off the Levantine coast in the east had dangerously loud volumes. The eruption shock wave extended outward about 80 kilometers, or 2/3 of the way to Crete. At 63 hertz, the sound is starting to attenuate. Most of the study area and all of the study sites heard the eruption in this octave. Places between 1,200 kilometers and 1,700 kilometers from Thera had relatively quiet volumes. It was loud between 9 and 1,200 kilometers from Thera, very loud from 600 to 900 kilometers, painfully loud from 300 to 600 kilometers, and dangerously loud from 60 to 300 kilometers. Inside of 60 kilometers, it contributed to the shock wave. At 125 hertz, attenuation is really hitting hard. Most of the study area would not have heard this octave. The area of loud sound has shrunk to cover the Aegean Sea, Greece, and Crete. Now, the area of 150 to 190 decibel sound shows the effect of the IDW interpolation on these space points 100 kilometers apart. You can see it really well in the inset where it forms a diamond-shaped pattern. The diamond pattern is very evident at frequencies of about 250 hertz and above. So I gave you 250 hertz as a representative. The others don't look very much different from this one at all. Now onto the visual side of excuse me, the visual side with the view shed. Unsurprisingly, the main effect on seeing a 41 kilometer tall ash cloud is the horizon. The eruption was generally visible in a circular area 780 kilometers in radius from Thera. The further away from the eruption, the more terrain plays a part in visibility, like here in Asia Minor or here in northern Greece. Ironically, the westernmost point that could see the eruption was Mount Etna over on Sicily. Out of the 39 study sites, 16 could see the eruption. So how do these results answer the research question? Well, first, what did it sound like? It sounded kind of like this, and I hope I did it right.
Watch out for the shock, it's coming.
Okay, it sounded like that times 1,000. This would have been the loudest thing these people had ever heard. A tremendous deep roar from the Plinian eruption, followed by loud thunderclaps that would have happened on and off as the surges hit. So who would have heard it? Everybody heard it in the study area. And they probably heard it from England to India to sub-Saharan Africa. What did it look like? Probably like this eruption of Mount Etna here on the left, or of Mount Redoubt in Alaska there on the right, except much taller. The further away from the eruption, the lower it would sink, until it looked like a tremendous thundercloud on the horizon. So who saw it? Well, 16 study sites, and most of the people from Italy to Cyprus would have seen this eruption. So, what else can be done? First, improving the model. This is a very basic study. I abstracted or ignored the effects of wind, air density, and sound on air density and terrain on sound propagation. More sophisticated models could take these variables into account. A great model would be able to scale up or down as needed, so small sites to big sites. Second, a view shed analysis of the extension of ash cloud may open a wider range of sites to the east. Finally, ground truthing, using the suggested search area from this study to look for sites with records, because after all, that was the whole point of this project. So here are my references in a blur. And thank you. Are there any questions?